The Keysight Genesys software includes a feature called Vendor Parts Synthesis, or VPS, that's intended to help users quickly design circuits using Modelithics models of real vendor components. A VPS-enabled design flow involves taking any design with RLC components and automatically replacing the ideal RLC component models with Modelithics models of actual manufacturer parts. Microstrip interconnects are also automatically added to the circuit. The circuit can then be optimized to meet the design goals. The end result is first-pass design success in a short amount of time. Before getting started, if you haven't already, you may want to check out the Modelithics Quick Start tutorial video for Keysight Genesys. Now let's demonstrate VPS to show exactly how the process works and why it can benefit designers. Note that the Modelithics Complete library is installed for this demonstration. For this example, we'll design a low-pass filter. So let's select Passive Filter from the Genesys workspace tree. We'll choose a Chebyshev filter, and we'll also select Minimum Inductor as the subtype. We'll design a 7th order filter with a cutoff frequency of 1500 MHz. Now we can see the synthesized filter schematic based on the parameters we entered. We can also see the frequency response. Note the cutoff frequency of 1500 MHz. Now at this point, we can use VPS to turn this initial filter design into a real-life design that we can actually build. So let's select Vendor Part Synthesis from the workspace tree. Notice the Vendor Part Synthesis Properties user interface that now appears. In the Vendor Part Synthesis Properties user interface, let's begin by selecting Configure Libraries. Here, we can select the Modelithics part libraries that we can use for the design. Notice the Modelithics Select Plus library is selected by default. The Select Plus library is a free sampling of Modelithics models that's included within the Genesys installation. You'll also see the available libraries from version 20.7 of the Modelithics Complete library. To request a trial of the Modelithics Complete library, visit www.modelithics.com. In this case, we'll only choose the Select Plus library. Now let's go to the Defaults tab. Here, we can assign specific part families for the capacitors, inductors, and resistors in the design. Notice how we can select the body style for the components. For this design, we'll be using 0603 size capacitors and inductors. Now, we can choose from the 0603 size capacitor and inductor part families available in the Select Plus library. We'll use the Chemet CBR06 series for our capacitors and the Coilcraft 0603 CS series for our inductors. Since there are no resistors in this design, we don't need to specify a resistor part family. You'll also see this info section at the bottom, which lists the range of part values included in the selected part family. Make sure that this part value range spans the range of part values you need for your design. If not, you may need to select a different part family. And finally, we can also specify the component tolerances. For now, we'll set the tolerance of both families to the default value of 10%. But we'll look at this more closely later when we perform a yield analysis. Selecting the Mapping tab lets us implement individual component mapping. Now we're not going to utilize this in this design, but you should be aware of it. So let's say you wanted capacitor C1 to be assigned a different family than the default Chemet CBR06 series we just selected. You could do this by unchecking the Use Default checkbox next to C1 and then selecting a different part series for C1. Also notice the Use Original checkbox. Selecting this enables the component to retain its original value. This option could be used if you want to implement a particular component as a distributed element. With this option, a component can be assigned any value without being limited to manufacturer part values. Again, We're not going to be using individual component mapping in this design example, but it is something you want to be aware of. Let's now click the Apply button. This will prompt us to specify a substrate for the design. For this filter, we're going to choose 20 mil Rogers 4350B from the Modelithics substrate library. We now have a VPS schematic that includes Modelithics models for the capacitors and inductors. Again, for the capacitors, we're using the Kemet CBR06 series. For the inductors, we're using the Coilcraft 0603CS series. Note that the models are set to the real-life manufacturer part values that are as close as possible to the component values in the original schematic. The original schematic can also be referred to as the reference schematic. We can take a look at the results after simulating this new VPS schematic. The magenta trace represents the simulated S21. For comparison, the graph also shows the simulated results of the reference schematic with the red trace representing S21. We can see that the frequency response of our new circuit is shifted downward in comparison to the frequency response of the original circuit. This downward shift is a result of using Modelithics models for real-life parts rather than ideal component models. Next, we'll need to generate a layout for the filter. Let's go back to the Vendor Part Synthesis Properties user interface. Here, we'll select the Layout tab. We'll then select Generate Layout. We'll also select Generate Momentum Analysis, which will allow us to perform an EM circuit co-simulation. We'll need to specify the dimensions of the microstrip interconnects. We can enter the trace width, the length of C-LNR connections, and the port connection length. Now, clicking Apply updates our VPS schematic to include the microstrip elements. We can see the simulated results of the updated schematic. Again, the magenta trace represents S21 of the VPS schematic, which now includes Modelithics models and microstrip interconnects. The red trace represents the simulated S21 of the reference schematic. We can see that adding the microstrip interconnects caused the frequency response to shift slightly further downward compared to the previous simulation results. Now, the frequency response of our filter is shifted downward by about 300 MHz in comparison to the original circuit's frequency response. So far, we've only performed circuit simulations. To ensure accuracy, we'll want to perform an EM circuit co-simulation. Now, to view the actual layout, we can click the Layout tab here. Let's now right-click the VPS momentum analysis in the workspace tree and select Run Calculate Now. Let's go back to the graph. Here we can view the EM circuit co-simulation results with the orange trace representing S21. The graph still shows the results of the previous VPS circuit simulation along with the simulated results of the reference circuit. We can see how the EM circuit co-simulation results deviate even further from the desired performance. So it's clear that our filter is not meeting our goals. Therefore, we'll need to optimize the design by adjusting the component values to the optimal values to achieve the performance that we want. To do this, we can click the Optimization tab in the Vendor Part Synthesis Properties user interface. The optimization process involves a continuous optimization followed by what's known as a grid optimization. A grid optimization is a grid search of the nearest component values. By default, the grid steps up and grid steps down parameters are each set to 1. This means that the software will search one step up and one step down in value. For this example, we'll just stay with the default settings. Now we'll click Apply and will then be prompted to specify the optimization goals. We'll set optimization goals of 1 dB for the passband transmission, 25 dB for the stopband transmission, and 16 dB for the passband reflection. Notice how VPS automatically identifies the stop band frequency range. So now we can just run the optimization. We'll let that finish, and then we'll take a look at our EM circuit co-simulation results. We can see that our filter is now achieving the desired performance. The design process is almost complete, but there is still one last step. This final step is a yield analysis, which will allow us to determine if the component tolerances are sufficient for production requirements. To do this, let's select Monte Carlo yield in the vendor part synthesis properties user interface. We'll then select generate yield. We can see all the components in our design, each with a tolerance of 10%. As you may recall, this 10% tolerance is what we specified earlier. Let's click apply, and now this VPS yield evaluation appears in the workspace tree. We can open the yield properties to set our yield targets. Let's just change the S11 target from -16 to -15 dB. Now let's right-click VPS yield and then select Run Calculate Now. A new VPS yield graph appears. We can see that we're only achieving a 20% yield, which is not sufficient. Let's go back to the vendor part synthesis properties user interface. Again, we'll select Monte Carlo yield. And now let's lower the tolerances of the components so that we achieve a better yield. We'll change C1 and C4 to ±0.05, and we'll change C2 and C3 to ±0.1. We'll change all the inductors to 2%. Click Apply, and then again right-click VPS yield and select Run Calculate Now. Now the yield is 100%. So the design process is now complete. Let's take a look at the bill of materials that VPS generates. Let's also compare the part values of the ideal component models in the reference schematic shown on the left with the part values of the Modelithics models in our final design shown on the right. There's a pretty noticeable difference in part values between the two. So this illustrates the difficulty of manually trying to determine correct component values in the lab. Of course, to validate this design process, we'll need to build this filter and compare the measured data to the simulated results. Shown here is an assembled filter with the same chemic capacitors and coilcraft inductors from the simulation. This graph shows measured data of two different filters, along with the simulated results of the yield analysis. We can see that the measured data agrees with the simulated results, so we validated the design process. So in summary, we've demonstrated the VPS feature within Genesys, which enables us to design circuits with Modelithics models for real vendor parts. We hope you enjoyed this video, and please consider using this design approach if you think it might help you. Thank you.